standing waves in air columns. We already saw how standing waves occur in a string, and we'll see similar pictures when it comes to standing waves in air columns. There will be similarities and there will be differences. An important difference that we should point out from the very beginning is that these standing waves are for sound waves, as opposed to standing waves on a string. This was the subject of a previous video. And if we talk about sound waves, this comes with some benefits. The speed of the wave is known, is whatever the speed of sound is at that temperature. So the speed of the wave is obviously the speed of the sound, and that is known, as opposed to the speed being given by the tension applied to the string and the mass density of the string. There will be another difference that we'll see shortly. It will be the distribution of nodes and antinodes, right? And we'll compare this to the distribution of the nodes and antinodes in a string. It is this picture that we are all too familiar with it, in which these were the antinodes and these were the nodes. So we'll see when we are done with this topic that there are similarities and there are differences, but for now we have to be aware that from the very beginning we are talking about different things, and the huge difference is that we're talking about sound waves, which means we are talking about longitudinal waves, right? The medium, the oscillations are air molecules, as opposed to transverse waves in the string, and where the particles that are moving was the string itself. So really there are many differences, but also maybe not so surprisingly there will be many similarities. So now let's focus on these sound waves in air columns, right? So standing sound waves in air columns. We already saw that when it comes to sound wave, I can look at this in two different ways. I can look at it as a displacement, a wave, or I can look at it as a pressure difference wave, pressure difference wave. And we already know that these two waves are out of phase. It's something we saw before. So it will not matter in the end which picture we choose. The results obviously will be the same. The wave behaves the way it behaves, and it will give certain results that are independent of the way I look at it. However, we should be aware that there are two different ways in which I can look at a standing wave when it comes to sound. So we'll deal with two types of air columns. The so-called open-closed and open-open. So this is an open closed air column. You see why we call it open, why we call it closed. One end is open, one end is closed. And this is what we call open air column. No explanation required. Now, if I look at a displacement wave in an open closed column, I can represent it like this. So this is the displacement wave, and notice when it comes to the displacement wave, right? Notice that at the end here I have a node. This is a node, and the reason for that is perhaps not so hard to picture. The molecules cannot move. The molecules are hitting the wall. So in the displacement wave view, this must be a node. Now, if I look at the pressure difference wave, it's perhaps a little easier to understand what happens at the open end. At the open end, I will have a node. And the reason for that is that the pressure inside is equal to the pressure outside. Otherwise, air would flow in or would flow out. So that means I have a change in a pressure difference of 0, which gives me a node. So if I want to work in the pressure difference wave view, at the open ends I must have a node. If I work in the displacement wave view, at the closed end I must have a node. And since they are out of phase, that will result to exactly the opposite view for the other wave. So for example, here the displacement wave at the closed end is a node. Well, if I go to the open end, that must be an antinode because the pressure has a node there. And similarly, if I bring the pressure wave and I'm looking at it at the end, well, this will have to have an antinode here because, maybe I shouldn't draw it there because it's not really there, because again, the displacement wave has a node there. So maybe we can put this together to see how it looks in an open air column. So if I go with a pressure view, I must have nodes here. So now I'm not sure how many loops I can squeeze in here. I guess I can squeeze in 2 into this picture. So this is the pressure view, pressure difference view. Look, I have the nodes at the ends that are open. And of course, if I want to go with the displacement wave, don't forget they are out of phase. So if I go with that, I have to draw carefully, keeping in mind that they are out of phase. So if here I had an antinode, here I will end up with a node. So the view will be like this. And then the wave will go like this. And I end up with this picture. This is the displacement wave view. They are opposite, but as we will see very shortly, they will produce the same results. And this is something we shouldn't be surprised. After all, things happen regardless of the way I look at them. the same thing is going to happen regardless of my interpretation of things. Right? So this is a very important conclusion, that for an open end and a closed end, and if I look at the displacement wave, and if I look at the pressure difference wave, right? So for the displacement at an open end, I will have an antinode. At a closed end, I will have a node. While for the pressure difference wave, at the open end, I will have a node, and at the closed end, I will have an antinode. And now let's get to work and see how these things work. Let's be a little more quantitative. So let's work with open-closed air column, and we'll borrow a lot of knowledge from the standing waves on a string. So if we work with an open-end column, it will look like this. It doesn't matter which view we choose. Let's work with a displacement view wave. Displacement wave, right? So if it looks like this, I must have a node here. So this will be how the wave looks like. I always know the length of the column. But there is an important difference here with respect to string, to waves on a string. If I drew something like this for a string, what I drew here would have been exactly the string. The string itself, remember, the string was vibrating, well, it was the seagull, right? While here, this is not how the air molecules vibrate, right? The air molecules vibrate left and right. Remember, sound wave is a longitudinal wave. So for a string, this picture was literally the string, while for a sound wave, this is not literally the air. The air oscillates left and right. So now if I look at this picture, I recognize that what I see here is a quarter of a wavelength. It's that big story that we agreed upon, that one bump corresponds to half a wavelength. So here clearly I have a quarter of a bump. Now if I want to go to the next harmonic, we'll see that shortly, although we are familiar with the term, I have to maintain the condition of having a node here and an antinode here. This must be true. So what does it mean? It means that if I go to the next one, that's okay. I can squeeze in a loop here, but then when I go here, I must have an antinode again. This must, this condition must be always satisfied. The antinode must be present. So then when I look at this picture, I see I have 2 quarters plus another quarter. I have 3 quarters of a wavelength. So it's clear from here that I can easily say that the length of the air column must be an odd number of a quarter wavelengths. If you wonder, would I have gotten the same results if I was looking at the pressure difference wave? Well, yes. So just for this case, let's look at the other wave, and then we don't have to do it twice. So if I'm looking at the pressure difference, I must have a node here, and because I had a node here, I must have an antinode here, right? So the picture will look like this. Well, as far as I'm concerned, it's the same picture, but looking in the mirror, so L is still lambda over 4. And just for symmetry reasons. If I look at the next one, which should be absolutely no surprise, I'm going to get the same result. I have a node here, I want an antinode here, so my wave will look like this. And clearly the L equals 3 lambda over 4 is going to be satisfied, and by extension L equals odd lambda over 4. A similar discussion can be had for open air column. And when I do that, let's stick with the displacement wave view, and there is no need to look at the other one, the displacement wave view. So I have an open. If it's open, remember I want antinodes here. So that means how can I have antinodes at both ends? The wave must look like this, and this is the fundamental. The node must be here. If I want to go to the next one, I have to maintain my antinodes here, so I have to squeeze in an entire bump. So I have to have nodes here, and you get the idea. In this case, the length of the tube will clearly be 2/4. In this case, it will be 4/4, right? A quarter, and another quarter, and we can go down, and we can say that the length will be even times lambda over 4. So for both types of air columns, V is equal to lambda F is going to be satisfied. This is not going to change. The speed of sound we know, so that means I can find the frequency as V over lambda. And now perhaps we can do a split screen here, open, and open, closed, and see what happens. So the frequency here, in this case, in the open closed, the frequency will be V divided by lambda, but lambda is 4L over odd, so divided by 4L over odd, or odd V over 4L. This is the condition, the frequency in open closed tubes. If we go here, frequency will be V over lambda again, but now lambda is 4L over even, and this reduces to even V over 4L. And this is really the end of the story. If we choose the lowest possible values, we will have the fundamental. So if we go with odd equal to 1, and if we go to even equal to 2, that will lead to the fundamental. In other cases, I cannot go any lower than that. And then when I change that, when I go to 3, 5, and so on, that will lead to harmonics. And here when I go to 4, 6, and so on, it will lead to harmonics. So as I mentioned at the beginning of this video, I have pictures that look similar to the ones on a string, to the standing waves on a string. For example, this is the picture that I'm talking about. If I look at this picture, and if I look at this picture, right, they look the same. So this was the picture for an open air column when I'm looking at pressure difference wave. but again, I can look at either of the two waves and I will get the same results and the same conclusion that we saw in a string. The frequency is quantized, so the frequency is quantized. Frequency cannot take any values, and we know by now what it means, right? Frequency is quantized, which means in the end the energy is going to be quantized. As we saw, it happened for a string. So to summarize standing waves, since we are at the end of this topic, when we saw standing waves, we saw two different types of standing waves. This is a good, hopefully, review. So standing waves, we saw standing waves on a string, and the characteristics of this wave were that first of all, it is a transverse wave, right? Another characteristic was that the string vibrates. We saw that the ends are nodes. The speed of this standing wave is square root of t over mu. And we saw in the end that the frequency and the energy are quantized. When we look at columns, we saw similar things, but instead of transverse, the wave is longitudinal. It is, of course, not the string that vibrates, that air molecules vibrate. The ends are nodes, the equivalent of the statement, right? The ends are nodes only for displacement wave. Otherwise, ends are nodes for displacement for closed ends, right? For closed ends. So there are restrictions now, while otherwise ends are nodes for, so maybe I shouldn't say only, right? Ends are nodes for displacement wave for closed ends, and something similar for pressure difference wave, for open ends. Then the speed is the speed of sound, whatever that speed is at the temperature, and frequency and energy, they all are going to be quantized as well. The standing waves have very important consequences in modern physics. They have two major applications. One is the electromagnetic waves. Waves in a black body are standing waves, and this led to Planck's constant and then to photons, and the rest is history. And then we have the wave associated with the electron in the Bohr atom. So the matter wave, the matter wave of the electron in the hydrogen atom is a standing wave as well, and that will have some important consequences. We'll get from there the quantization of the energy of the hydrogen atom in the Bohr model, the famous negative 13.6 divided by n squared electron volts. So these modern physics concepts, from the beginning of modern physics, from the beginning of quantum mechanics, the electromagnetic waves in a black body and the matter wave, the one that we saw that it is associated with any particle in the hydrogen atom, they are standing waves. And this is why in the end, when people study these things in quantum physics, and when we get these quantities are quantized, that they can have only certain values, they are quick to point out that this is not a consequence of doing quantum mechanics. This is actually a consequence of boundary conditions. This is a consequence of boundary conditions. And we saw that in greater detail in the string standing wave, in which we found the energy was quantized, but that has nothing to do with quantum physics. That has to do with the boundary condition by forcing the ends of the string to be nodes. And something similar, of course, happens in standing waves in air core.